So in this video, I wanted to go over homework problem 7.15 with you. We have a beam that's subjected to a distributed load. It's uniform from 0 to 3 meters, and then from 3 meters to 9 meters, it linearly tapers off to 0. We have the magnitude of the actual uniform portion of that load. The density is 6.5 kilonewtons per meter. And what we're asked to do is to find the internal forces at point C and follow a sign convention. So what we notice is if we pass a vertical section through point C, the left portion will not be statically determinate. And the reason is, if we were to do that, that left portion will not only have, let me get it drawn here. So this is from A to C, and this is 3 meters in span. And what we notice is that if we follow the sign convention and we draw our internal force system, namely the normal force or axial force going out, it is unknown, the shearing force going downwards, and the bending moment going counterclockwise. That in addition to having these three unknowns, which are all that we could ever hope to solve for in a coplanar force system where we only have 3 equations of equilibrium, we will also have 3 unknowns associated with this reaction. So you could call this AY, AX, and maybe MX. And you can assume whatever sign convention you want because, sorry, I should have called that MA. And the reason that we really don't care about whether the thinking about the sign convention or any of that is these are an additional 3 unknowns, so this is statically indeterminate. So if you were to have a problem where you actually were interested in solving for the reactions that that point of connection at the wall was subjected to, you would have to actually analyze the right portion of the beam first. And the reason that we would actually analyze the right portion of the beam, which is going to go from point C out 6 meters to point B, is that this system, or this body, is statically determinate. Namely, if we draw in our internal forces, normal force by Newton's third law going to the left since this one went to the right, shearing force going up since the other one went down, and bending moment going in the clockwise direction. What we notice is that these 3 forces are, of course, unknown. However, the only other forces that act on this portion of the beam are known. They're just going to be the distributive force, which is acting from C to B. So the first thing that we're going to want to do is to replace that distributive force by a single equivalent force. So using the same convention that we usually do, if I have a distributive force, which is tapered in a linear fashion, and it has a peak value of 6.5 kilonewtons per meter, and it's distributed over a span of 6 meters, we note that the actual magnitude of that equivalent force is simply going to be the area under this density function. And since this is triangular, we don't even need to integrate. We can just take 1/2 the base, which is 6 meters, times the height of the triangular load, I should say, which is 6 kilonewtons per meters. Notice that, of course, the units of meters cancel, and I'm going to get something that's purely in kilonewtons. And if I do that math, what's it turn out to be? 19.5 kilonewtons, I believe. So that tells us how big the single equivalent load should be. Now the question is, where should we place it? Well, remember, for a triangular distribution, what we're really looking for all shapes is the centroid, or the center of mass, of a uniform plate that would be formed by that density function. Another way to say that is the centroid of this triangular shape. And we're moving to the point of the course where we're actually going to determine those through integration very quickly. However, for now, we just assume that it's something that we can look up in a table. And we know that for a triangular distribution, 1/3 of the base from the fatter portion is actually where we're going to place that load. So if this entire triangular distribution is distributed over 6 meters, 1/3 of that would be 2 meters. So I'm going to place it 2 meters to the left of the actual start of that load. And we've already said that the magnitude would be 19.5 kilonewtons. So how do we actually go about solving for the internal force system, which is what we want to find? Well, we notice that there are no forces acting in the horizontal direction other than that axial or normal force. So that tells us that there's actually no internal normal force in this case. If we were to sum all forces in the y direction and set those equal to 0, what we would find is that we have the shearing force, which is kind of an ugly V here that I've drawn, going in the upward direction. And then we have the 19.5 kilonewton equivalent load going in the downward direction, and those must counterbalance one another. And what that tells us is we have a 19.5 kilonewton shear force directed in the positive direction according to that sign convention that we spoke of previously. If we sum all moments about C and we use a counterclockwise positive convention, in order for this to be in equilibrium, The sum of all moments must be equal to 0. Notice that by our standard sign convention, the internal moment here is going to be in the clockwise or minus direction. And if I were to pin at C and actually rotate that 19.5 kilonewton force, what we notice is that 19.5 kilonewton force also induces clockwise rotation, so it's going to be negative. So I'm going to have minus 19.5. That is the magnitude of the force. The perpendicular distance, or the distance from the point of interest to the line of action of the force, is just going to be 2 meters. We get 19.5 kilonewtons. So what that tells us is that the internal bending moment is actually going to be negative, meaning that this isn't inducing bending. It's actually introducing bending in the concave up direction, rather. So what this turns out to be is just going to be minus 2 times 19.5. And that is going to be, I shouldn't do this in my head or I'll regret it and I'll probably make a mistake and have to redo the video, but I'll trust myself that it's minus 39 kilonewton meters. So hopefully that makes sense to everyone of how you compute those three forces. Pretty review, that's kind of very similar to the problem that we did last week, where we, in addition, were able to pass a section and able to get a statically determinate system that only involved the unknowns of the internal force system at the point where we're trying to solve. So what we're going to do now is transition order into a technique of finding an expression, a graphical expression for the internal force systems over entire beams, and that's known as shear and bending moment diagrams.